Good afternoon. Today I'm going to be talking about the CPU with a possible digression into GPUs, because they really aren't too different from CPUs. I'm sure you have bought a PC in the past, a laptop maybe, and one of the things that you look for is a really good CPU. So say you're looking at various spec lists and you see like 3 gigahertz and various things like hyper-threading. I've run out of space there, so I'll just do it here. Hyper-threading and all kinds of other weird and wonderful words that don't typically mean much to most people. You know that like more gigahertz is better than fewer gigahertz, but really it's hard to tell whether a CPU is good just based on the spec list. But we're going to wind back from that a little bit and talk about what a CPU does first. So the analogy people usually draw is that the CPU is to the PC what the brain is to the human body. And it's a little bit of a fluffy comparison, but I think that the core of it is correct. So the CPU is what decides what happens in your computer, when you boot your machine, and when you move windows around, and when you play games and double click on things, all of that stuff runs through the CPU. The CPU is the kind of central arbiter of the things that are going on in your system. There are things that do happen that don't involve the CPU, but these things are definitely a minority. Very similar way to how a lot of things go through the brain. So you don't typically move your arms or speak or anything like that without your brain being somehow involved. So again, the brain is also very much involved in what happens in your body. And again, there are many things that happen in your body that don't go through your brain. There are things that can't go through your brain because your brain would just be a bit too slow. So that's what the CPU's responsibilities are. It basically does and decides everything. It runs programs, it makes decisions. When you write programs and you write code, that code is going to be executing on the CPU usually, if it's not executing on some more specialized piece of hardware like the GPU, for example. But what is it actually doing? So there are two predominant schools of thought when making a CPU. So we have lots of different CPU manufacturers in the world. We have Intel, who are by far the largest. You have ARM, who specialize in low power, high efficiency chips. Various other companies, so you also get PowerPC less frequently, but still used in supercomputers and things like that. I'm trying to think of more chip manufacturers. I think Apple designed their own chips, but they don't make them. I think they're made by another company. No, I think I'm drawing a little bit of a blank. That these, AMD. But now that I've said that, I'm wondering, do they just make GPUs? No, I think they make CPUs as well. Intel is the main one. ARM is also a very big player, and these people exist, but they're to a much lesser degree. They're not as common as Intel and ARM. So one of the key components in a CPU, not a physical thing, more of a logical thing, is the instruction set. this is going back to what I was saying earlier about there being two main schools of thought. So you have what are called RISC CPUs and you have CISC CPUs. And ISC stands for Instruction Set CPU, and the R stands for Reduced, and the C stands for Complex. So you have Reduced Instruction Set CPUs, which offer a very small number of quite simple instructions, and it is the job of the programmers to come up with more complex operations based on that. Then you have the complex instruction set CPUs, where the CPU instruction set will offer quite complicated instructions. And what does that really mean? So an instruction, we'll start with the basics. So the instructions do a thing, and I realise that's kind of an abstract example, so I will say move 6 to 0x 1000. Right. Slow down, Sam. This is very complex. What's happening? What's going on? So we have, this is the actual instruction. And it does what it says. It's a move instruction. Then what we have here are what are called operands. And these are the things the instruction is operating on. So the 6 here is simply the number 6. There's nothing special about that. It's what we call a, the word escapes me. There is a way of referring to just numbers in code. I think it's something like an integral constant or something like that. It's irrelevant. It is a 6. And then this thingy here in square brackets is a location in memory. But what is it, like 0x1000? What does that even mean? So square brackets simply tell the CPU that this is going to be a memory location. And we said in a previous video that CPU can communicate directly with memory. So it loads things into memory and it retrieves things from memory, and that's one of the basic things that a CPU can do. So the 0x is a very common prefix in program code that says the following digits are hexadecimal digits. So we spoke about hexadecimal in the bits and bytes video. If you haven't watched it and you don't know what hexadecimal is, I recommend watching the bits and bytes video and pausing this one for a moment. So this 1000 here is not actually a decimal 1000, it is a hexadecimal 1000. I'm not going to calculate, I wouldn't trust myself to calculate what the decimal version of this is, but if you recall from, I think in the previous 2 videos we've discussed this, where memory and storage in general, be it a hard disk, RAM, solid state drive, they are all large arrays of contiguous bytes. And when I say contiguous, I mean they're laid out physically next to each other. So you would have cells one after another. And if you refer to them all with sequential numbers, so for example you'd have cell 0, cell 1, cell 2, cell 3, cell 4, cell 5, cell 6, and so on, way up into the many, many billions, because that's the kind of scale that we operate with memory. All this is saying is take the number 6 and move it into the memory location denoted by this number. And this will be quite a large number. Off the top of my head, I can't quite tell what it would be, but I think it would be tens of thousands. And that is one of the primitive operations that a CPU can do. It can move something into memory. And the opposite is also possible. If we want to get that back out of memory, we would say move from 0x1000, oh, it's a very small 0, into, let's say, I'll say EAX. I think the percent symbol goes beforehand. The only new part here is whatever the hell this thing is, right? What does percent EAX mean? Well, the CPU can talk directly to memory, but it can't do operations to things directly in memory. It needs to first load them out of memory into its own memory. So the CPU has a very, very small bank of memory on itself called registers. It also has a bunch of caches, which we spoke about again in bits and bytes. We'll ignore them for now, but just imagine the CPU has a few hundred bytes of its own memory, and EAX is the name of a register, and this register would be 32 bits or 4 bytes in length, and it would be very specific to Intel CPUs. When you are operating at this level, this is quite a low level to be writing code at. People don't typically write instructions directly, not anymore. But way back, many decades ago, people would be writing what this is called assembly code. And people used to write this directly because there weren't any other programming languages to write in, or there were some, but they were very new and perhaps not that reliable. So people would just write instructions directly to the CPU, and one of the problems with doing that is these instructions are very specific to Intel CPUs. Some AMD CPUs also support them, but for example the ARM CPUs, their instruction set looks very different. This would not work on ARM CPUs. Same goes with PowerPC. They have different what are called assembly languages. Because the CPUs themselves are very different, the assembly language is quite specific to the way that each CPU works. But this would just move the value from 0x1000 in memory into the register EAX, which again is just a small bit of memory on the CPU itself. That's a very kind of like abstract and simple overview of how a CPU instruction works. Once we have a value in EAX, let me just clear the screen here. Once we have that value in the EAX register, what we want to do next is actually do something useful with it. And the CPU has a bunch of instructions to help us with that. Let's say we wanted to double the number. We have two options. We could add EAX to EAX. And that's kind of one of many ways to multiply a number by 2. You could also multiply EAX by 2 specifically, and you can change this to whatever number you want. You could say 10, multiply it by 10, for example. And when people talk about computers being just a very, very quick sequence of mathematical operations, this is the kind of thing that they're talking about. And it's true. CPUs don't do anything too much more complex than what we're seeing here. All of the more complex instructions they're either doing a common sequence of things, or they are doing the same thing to lots of pieces of data in a more efficient way. But in reality, all that's really going on under the hood is things get loaded from memory, manipulated in some way, and stored back out to memory. The only other thing a CPU does is talk to other pieces of hardware. For example, the screen. We spoke in the previous episode that an image is just a grid of bytes. And that's kind of the same for screens. we spoke in bits and bytes about the way that colours are represented in images. It's the same on a screen. You have 1 byte for the red component, 1 byte for the green component, and 1 byte for the blue component. So if we wanted to represent red, we would put in the highest hexadecimal value we can for red, and then 0 for green and blue, and that 3 byte sequence would represent the colour red for a particular cell. And this is how screens work as well. So a screen is a really dense grid of what are called pixels. A pixel is just a fancy way of referring to a single cell on a screen. The only real difference is that there are lots of them, right? So when you have lots of small cells, you can set them to different colours, and because it's so dense, we trick the eye into thinking that it's a real, like, bona fide picture that's being shown to us, and it ends up looking pretty good. So the way that the CPU ends up putting images on the screen, now I'm going to caveat this with this is a method of doing it, and it typically doesn't work like this anymore, but it's a simpler explanation. That there are more kind of specialized video drivers now that do wacky and wonderful things to make the viewing experience better for the user. But when your machine first boots up, for example, and it displays, say, a logo on the initial screen, this happens before these sophisticated video drivers have been loaded, and what I'm about to describe to you is how this actually works in that boot phase. But we moved away from this because it's not particularly efficient. So this grid here, which is currently representing a screen, imagine that we had a region of memory that of the exact same size, essentially. So if we have our 16 pixel grid here that shows images, let's say we have a 4x4 screen, we would also dedicate a 4x4 section of memory to represent that screen. And every roughly 16 milliseconds, we would copy this to the screen. The CPU would take all this data here, and it would send a message to the hardware through the HDMI port or whatever, saying these are the next 16 bytes that I want to show you on the screen. So if we made a change, let's say we've got this red thing here, and we run some commands. Let's say let's say this is 0x1000. This is 1001. We say move 0x00ff0. Oh, whoops. 1 2 few f's. ff00 into 0x100. Because it's 3 bytes, actually we need to move to 1003. My bad. So we did mention earlier the 0x prefix just tells the CPU that this is a hexadecimal number. We haven't wrapped this bit here in square brackets, so it won't be a memory location, whereas this one is. So we're saying take 00ff00 and store it in 0x1003. So what that does is it puts a green color in here, and then at some point in the future this grid gets copied to here, and your screen will display a green square as well. And the only real difference between this and reality is that in reality these grids are much bigger, but that is kind of how screens work. The way that a CPU, one of the commands that CPUs have is they have one called out, and they have one called in. There are various. If you've looked at your motherboard, there are various connectors on it. So, for example, there's a slot that you plug in your graphics card. There are slots for you to plug in sound cards. There are slots for the RAM. There are various things, right? So PCI slots for your expansion cards, and so on and so forth. The out and in commands. Out is send some data to a port, and it will be one of these ports. And in is read some data from one of these ports, and any kind of sound card or graphics card that you plug in will expect certain commands from the out instruction of the CPU, and depending on what you ask it for or tell it to do, it will give you results with the in command. So let's say, for example, our screen is on, so the ports are all numbered. So let's say our screen is port 1, and if we want the screen to refresh, and we want whatever is in this grid to be copied over to this grid, maybe we have a screen that is expecting the number 10 and sending it the number 10 is basically telling it to refresh the screen. So we would say out 10 port 1, and that would send the value 10 to port 1. The screen would receive that and it would go, okay, cool, right, I'm being refreshed. Copy all that data from the grid in RAM. I should probably label these RAM screen, and then it would display the new values on the screen. And again, it is simplified, but it is very much in spirit what happens. It's just that what happens is a little bit more involved. The out and in commands you have to do are a little bit more complex. I forget exactly whose responsibility it is to copy it. So when we have like segments like this in RAM that are dedicated to a specific purpose, we call them buffers. So I don't know whose responsibility it is to copy the buffer over to the screen. I would imagine it's probably the CPU. So instead of the CPU giving it a command to tell the screen to read a bit of RAM, what it probably does is it will issue a command that says, I'm about to send you a new screen buffer. And then it would send all of the individual colours cell by cell over to the screen, and then it would send another command that says, I'm done. And when the screen receives the I'm done portion, it would probably redraw the screen with the new values. So this is not entirely 100% accurate, but the spirit of it is very much there. And that is how the CPU talks to pieces of hardware. Your sound card would be very similar, for example. You would just send sound data instead of image data. And the representation of sound data is quite different. It's not something I know in much detail, I'm afraid, so I can't go over it. Also, it would be a little bit off topic. Alright, we've rambled on for some time about how the CPU does its thing, talks to other pieces of hardware and so on. So how does it really differ from a GPU? Like, why do you need a GPU if the CPU can draw to the screen and everything's great? The answer to that is that the GPU is essentially the same as a CPU. It's just a bit more specialized for doing graphical commands. So CPUs are general purpose, and they try and be pretty good at a wide range of things. The GPU was designed because when you're drawing things to the screen, because inherently a screen is a grid of numbers, and when you draw a frame on the screen, and a frame is just a snapshot of what the screen looks like, so it's this big grid of numbers at one point in time, you will probably end up doing 16 of roughly the same operation, or however many pixels you have. It's just in this example we have 4x4 as our screen. You end up doing the same operation to 16 times, just to different bits of data. And when you scale this up to bigger kind of real screens, like 4K for example being the new in thing, you have millions, tens of millions of pixels, and you end up doing the same operation tens of millions of times. And CPUs do things typically sequentially, so a CPU could have more than one core. So if you have like an 8-core or an octa-core CPU, your CPU can be working on 8 different streams of work. So we spoke about when we do a move this, add this, multiply that, your CPU will do those in order. And a core can be working on one set of instructions in order at a time. And having 8 can make your operations 8 times as fast, provided those operations are all exclusive from each other. So you don't have a calculation that depends on the result from a different stream of work. So let's just visualize this a little bit, because it is important to how GPUs work. Let's go back down to 4. So we have each one of these lines represents a CPU core. So we'll say core 1, core 2, core 3, core 4. And when I say core, when anyone says core, all they really mean is it's essentially another CPU. So a 4-core CPU is actually 4 individual CPUs that are just interlinked, so they can communicate with each other if they need to share data between cores. But 4-core CPUs are typically just 4 separate CPUs. So we have 4 cores here, and if we have 4 completely isolated calculations, let's say we're taking 100 numbers and we're doubling all of them and then print out the result, we can be doing 4 double operations at the same time for each. As we go through this this list of numbers, we'll be doing 4 operations at a time, complete the task 4 times faster, everyone's happy. But 4 is not really gonna cut it. Like if you have huge images you need to process, and in graphics you are typically doing the same operation just across all of the pixels, you really need more parallelism. CPUs run pretty quick. They have, so whenever you see like 3 gigahertz, this is referring to what's called the clock speed. Which interestingly over time has meant a bit less every year, because inside your CPU there is essentially, okay, this could be outdated knowledge, this is like circa mid-2000s from when I first learned about this, but there is something that it vibrates at a given frequency, similar to the way that watches have quartz crystals in them that vibrate when electricity is passed through them. I think CPUs have something very similar inside of them. And 3 gigahertz means this thing vibrates 3 billion times per second. And it acts as a way of synchronizing operations across the CPU. So instructions will take a number of clock cycles. A move instruction, let's go with add. Let's say an add instruction takes 1 clock cycle, like it's really quick. The CPU doesn't move to the next instruction until at least the next cycle. So if something took 2.5 cycles, it would actually take 3, because the CPU uses this constant speed vibration to synchronize the operations inside of itself, so that you don't get electrical signals crossing over each other and corrupting the result of calculations and things like that. So in a way, the clock cycle does refer to how fast a CPU can perform operations. In reality, this isn't true, because instructions can take multiple clock cycles, and a clock cycle is just one iteration of this vibration, which it does 3 billion times a second. So what people have started to measure is something called IPC. It stands for instructions per cycle. And I don't know off the top of my head what the current good numbers are, but I'm led to believe that if you're completing one instruction per cycle on a single core, you're doing very, very well. There are so many things involved that will what's called stall the CPU, so it can't do anything. For example, reading a value from memory takes multiple hundreds of clock cycles, and in that time, the CPU, it likely isn't doing anything. People that make CPUs try very hard to avoid these kind of CPU stalls causing problems, so they will do things what's called out of order execution, OOE. So if they see that you've got a couple of, if you're doing, say, a move from memory into a register followed by an add, followed by another move from memory into a register followed by a multiply, it will actually swap these two instructions so that the moves happen first. And the reason is it wants to kick off the it wants to kick off the loading from memory as early as it possibly can, because it knows that that's going to take the longest. It's even clever enough to know that if you move from somewhere in memory to EAX, then add, and you move from somewhere from memory into EAX again, and you multiply, it's clever enough to recognize if there are other free registers that aren't being used. It will say, right, these two moves are going to the same place, but I could save some time if I put this instead into EBX, because nothing else is using EBX, and I really want to kick off these loads from memory as fast as I can. The CPUs are wickedly clever. The people that make them even more so. I remember reading somewhere that, so if you've ever seen a CPU, I really wanted to get one to show on camera, but I didn't feel confident removing my own. They're just like small rectangles. They're maybe, let's see if I can, they're maybe about that big. They're not very big, but 99% of the space on a CPU is dedicated to these kind of optimizations. And only 1% is dedicated to actually doing work. The rest of it is just figuring out how things can be optimized, because there are so many things that can stall the CPU that you want to avoid. Anyway, I digress. This is a topic I love so much, but GPUs are just a specialization. Instead of having like 3 gigahertz clock speed on 4 CPUs, a CPU instead would like to have, say, I actually don't know what the real numbers are, but they would do something like 1 megahertz clock speed on 1,000 cores, because there is so much win to be had on doing the same operation many, many, many times in parallel. So GPUs just totally optimize for parallelism over any kind of like individually fast cores. But under the hood, they do mostly the same things as CPUs. The main difference is that they typically optimize towards what are called floating point operations. So earlier on with our CPU example, we were just adding, say 6 plus 4 is 10. These are integers. And we saw in our bits and bytes video that representing integers in binary, relatively simple. But what if we were doing like 0.3 plus 0.7 equals 1.0? These are called floating point numbers. And they're a bit more tricky to represent in binary. I encourage you to take a second to just think about how you would represent a floating point number using just zeros and ones. Okay. The way that it typically works on a computer is, now I need to very much be a little bit careful here, because I'm sure people will point out if I do this wrong. But a typical floating point number, I'm just going to write I, E, 7, 5, 4 in the top. And if you are like super interested in this topic, this is the international standard for representing floating point numbers on computers. If you're not asleep by now, this will definitely put you to sleep. So a floating point number is typically 32 or 64 bits, but I'm going to talk about the 32-bit one first. So let's draw a set of 32 bits. Now, we can get there by halving. That's 4. This is 8. I feel like I'm not going to have space. 16. I think I'm going to have to draw a line through the middle. And then 32. Okay, the way IEEE 754 describes that we represent a floating point number is through essentially a calculation. And that calculation is the first bit represents the sign. So 0 would be positive, 1 would be negative, or vice versa. I forget which way around it is. So we have sign. Then the next 8 bits, 4, 8, are what's called an exponent. I will explain what these mean momentarily. Just do colours and say that sign, then exponent. Then the remaining bits are kind of esoterically referred to as a mantissa. And I'll be honest, I don't really know what that word means outside of this context. I'm assuming it has some mathematical meaning. So you have mantissa. And these three things become part of a equation called, let me just get this correct, I think it's -1 to the power of the sign plus 1 plus mantissa to the power of the exponent. This, I'm sure, still means completely nothing, but so being 8 bits, the exponent can be between 0 and 255. In reality, what they do is they subtract 127 from it so that we can represent smaller numbers as well, because raising something to the power of a negative number makes it smaller, right, rather than larger, and you can represent decimals and whatnot. The mantissa is actually a fractional value for this exact reason. So instead of being 2 to the power of 0, 1, 2, 3, 4, and so on, it's 2 to the power of, I don't think there is a 0, I think it's 2 to the power of -1, 2 to the power of -2, -1, 2 to the -2, 2 to the -3, and so on. And a brief refresher of how you do exponents that are negative, like something to the power of negative something, is it becomes, so instead of 2 to the -3, you can write that as 1 over 2 to the 3, or 1 over 8. And that is simply how you do negative exponents. So this goes all the way up to 2 to the power of -23. You take that fractional value, you add 1 to it, you raise it to the power of the exponent -127, then you, it's multiplied by, not plus, sorry, multiplied by the sign bit to say whether it's positive or negative. Now this, you can see, is way more complex than doing integer calculations. as a result, it requires more specialized hardware. So typically CPUs will have what's called a floating point processor, a floating point, I think they call it an FPU. That's a float processing unit or something like that. It's a specific part of the CPU that deals just with floating point numbers. And the GPU, because almost all graphics is done using floating point, very, very little of it is done using integers. The GPU is very specialized towards floating point numbers. And the 64-bit version of this just has a slightly larger exponent and a much larger mantissa. I think the exponent for a 64-bit, what they call double precision floating point number is 11 bits, and then you just have way more mantissa, and the precision you can get is much higher. So as well as being called floating point numbers, these are also called arbitrary precision numbers. And the reason behind that is that because this formula can't actually represent every floating point number, that would be impossible, because theoretically there are an infinite number of numbers between 0 and 1, and then there's another infinite amount of numbers between 1 and 2, and so on and so forth, and you can't possibly represent all of that precision. So what the typical guidance is that you're probably not going to get much more than 6 decimal places of precision from a floating point number. I don't think if that's the exact guidance, but it's ballpark, it's close. And it's better at representing small numbers more accurately as you get larger. I suppose I should probably say significant digits. It can do a number of significant digits. As you get to larger numbers, the numbers after the decimal place become less precise. Up to the point, I think, at 2 to the 53, you start actually not being able to represent all of the integer values as well. So there'll just be parts of the number line that you can't hit, and that's just the way it is, right? It's not an exact science. This is just approximating floating point numbers to the best of its ability inside of 32 bits. Okay, cool. That was a brief detour into GPUs. I just want to loop back to CPUs very briefly, because I did mention that I would talk about hyperthreading, and hyperthreading is a very simple concept. That sounds way more scary and complicated than it actually is. So let's say we have our 4 CPU cores again. We have C1, C2, C3, and C4. And we have a single stream of instructions flowing through each of them. At some point, a core will stall. Say if it's reading from RAM, or God forbid, is waiting for something from disk, because disk is so much slower than RAM. It will be stalled for probably quite a significant portion of time, multiple hundreds of clock cycles, maybe even thousands of clock cycles. This is a bit wasteful, having a core wait for the result of something slow is absolutely a waste of all of that time. So some clever person at Intel thought, what if we run 2 streams of instructions through each core? Wouldn't that be a pretty simple way of filling in the gaps? And some other clever person was like, that sounds pretty good. So let's just visualize a single core. So now we have a 1 core. But what they do, if hyperthreading is turned on, what actually happens is this 1 core is exposed to your operating system as 2 cores. So inside of C1, we have VC1 and VC2. This stands for Virtual Core 1, Virtual Core 2. So literally all it's doing is it's kind of lying to your operating system. It's like, yeah, no, there's definitely 8 CPUs here. Don't look too hard. There's 8. There's 8. Don't think about it. Then your operating system's like, oh, okay, cool. And it just uses them like it uses normal cores. It just throws instructions into them, gets results out, and the CPU itself deals with, interleaving the instructions in some sensible way. So you can't have a core waiting for another core for too long, so that it does some kind of like sharing of time between them. And when there's a stall in one, the other core can progress as normal. And if there's a stall in both of them, bad luck. But typically this results in approximately a 30% speed increase when you consider throughput of the CPU. So it's not the same as having 2 individual cores, but it's faster than having a single stream of instructions going through one core by about 30%. And that is all hyperthreading is. You almost always want to have it turned on. There are very few use cases where you would need to have it turned off, and in those situations you would probably know that you need to turn it off. If you don't know why you're turning it off, you probably don't want to. It is in general a very beneficial thing for the overall performance of your system. And I think that's about it for this video. Spoken about CPUs, brief detour into GPUs, a little bit of extra bits and bytes talk with regards to floating point numbers. Thank you again for joining me. If you've watched the rest of the series, thank you so much. I really appreciate that. And I will see you